Thank you.
Part 2, Arnold diffusion.
So, okay, so I want to complete what I discussed last time, in the sense, well, last time was announcement of the result, and well, I stated the basic theorem, which involved three subsets of, I guess it's C4 of let's see. So there was L equals, there was a Lagrangian, L equals L0 plus epsilon p, and L0 is contained in C4 whatever. Let's see. L0 is a mapping from B2 to R, and B2, I said I took B2 to be a ball in R2. Actually, I could take B2 to be a compact convex subset with smooth boundary and non-empty interior in R2 also. And then I take P as a mapping from T2 cross B2 cross T into R. So L0, so L0 is contained in C4 of B2 and P. Well, I was trying to do these with minimum differentiability hypotheses, so this is the best I was able to do. I think I can do C3 plus epsilon, but I didn't write that out. Anyway. So in C4, I announced that in C4 cross B2 cross C3 D2 cross B2 cross T, this contains three subsets, U, V, and W. So U is open and dense and positively homogeneous, and V is cusp residual with respect to U, and W is open and dense in V. And then I said I can tell more or less explicitly what U is. And I started on this project of saying what U is. And so what I want to do is I want to complete the discussion of what U is. Okay, so what is U? So this is the first part of my lecture, perhaps the whole lecture. Okay, so let's see. I should say that this depends on, the definition of U, V, and W depends on certain things. So I was discussing a version of Arnold diffusion, which a strong version where you have a family of open subsets, U1, UK, contained in B2. Actually, I want to, well, okay, contained in B2. Open and dense, open and non-void. And I want to be able to, I want to say that if I have an element of W, so if my Lagrangian is in W, so I have a Lagrangian in W, and associated to that I have an Euler-Lagrange equation. And I wanted to say that if I have that Euler-Lagrange equation, then I can find orbits which visit all of these open sets U1 up to UK. And the way I propose to do it is to construct various resonant intervals and then sort of diffuse along the resonant intervals. So we have resonant intervals, gamma 1, gamma 2, gamma 3. In general, you have enough resonant intervals so as to have a connection between any ui and any uj. Now, the idea is to then diffuse along these resonant intervals, and really the u's are associated to the resonant interval, so I can, in fact, I'll take as definition u equals u gamma 1 intersect u gamma k, and likewise for v and w. So what I have to do is, so to define u gamma, for example, u, for example, it's enough to define the u gamma i's. So I'll take. So this is what I want to tell you about. So I take a gamma, a resonant interval, contained in the interior of B2, and then associated to that, I have u gamma. So the question now becomes, what is u gamma? So if I answer this question, I told you the answer to that one because I have this definition that u is the intersection of the u gamma i's. And okay, so last time I started on this project of telling you what u gamma is. So associated to gamma, so last time, let's see. So I have to say what the resonance is. So gamma, by definition, gamma is contained in the set of omega 1, omega 2, such that k1 omega 1 plus k2 omega 2 plus k0 equals 0, where k1, k0, k1, k2 are contained in Z3, and k1, k2 is not equal to 0, 0. So this is the resonance, and you can assume, of course, that the greatest common divisor of k0, k0, k1, k2 equals 1. Okay, so and then for that we have the average system. We have average Lagrangian L gamma omega. Okay, so I defined it last time. I won't repeat the definition. Gamma k omega plus p gamma omega. This is a Lagrangian, the state space of this Lagrangian. So let's see, I should tell you what the state space is. First of all, I have something which I call T 2 gamma, which by definition is a set of theta 1, theta 2 tau contained in T2 cross T such that K1 theta 1 plus K2 theta 2 plus K0 tau is congruent to 0 mod 1. Okay, because of this condition, this is a 2 torus. I guess it's also, I think I have to use this condition to know that it's a 2 torus and not a finite union of 2 tori. Anyway, it's a 2 torus. Okay, and then I have T2 gamma is equal to T1 gamma. T1 gamma is equal to T2 cross T divided by T2 gamma. So this is a 1 torus. And it's the state space of L gamma omega. And L gamma omega is defined for omega contained in gamma. So L gamma omega is a 1-parameter family of Lagrangians. So this is, let me put here 1-parameter family. Okay, so this is sort of this procedure of averaging is very well known in this subject. Anyway, so I had so I have a list of, I said last time 12. I wasn't sure of the number, but anyway, in my preprint I wrote 10 conditions, so should have been 10, not 12. So I have this list of 10 conditions which define U. So there are conditions on, well, there are conditions related to this average Lagrangian and another average Lagrangian, which I'll discuss in a moment. So, so the conditions on this average Lagrangian I called C1, C2, C1. Well, C1 is that for each omega contained in gamma, L gamma omega has at most two local minima, two global minima, sorry, global minima. I may be putting them in different order from last time. C2, I'm not sure which order. Anyway, it doesn't matter. Each global minimum is non-degenerate in the sense of Morse. And
in C1 it's P.
P. Thank you. And C3 is transversality. So this is if omega 0 has two global minima, m omega 0 and m omega 0 prime, and m omega and n omega prime are their continuations to local minima for omega near omega 0, then d omega of p gamma omega at m omega, evaluated omega equals omega 0, is not equal to d omega of p gamma omega of m omega prime at omega equals omega 0. Okay, so these were the first three conditions. Now, the other conditions all have to do with averaged at a strong double resonance. So we say that gamma is an interval in a rational line, and such an interval contains a dense subset of rational points. So you say a point is rational if both omega 1 and omega 2 are rational. So saying a point is rational is the same as saying it has a double resonance at that point. So we consider omega contained in gamma, so it's omega 1, omega 2. So a second resonance is L0 is L1 is L1 L2 L0 such that L1 omega 1 plus L2 omega 2 plus L0 equals 0. L1 L2 L0 contained in Z3, and again L1 L2 not equal to 0 0. So same conditions, and we can assume, we can always assume without loss of generality that the greatest common denominator of L1, L2, and L0 equals 1. Yeah, actually, I'm not sure. Now I'm not sure whether this is an extra condition. Actually, I want to assume that the group yeah, right. The vector is independent. Yeah, thank you. And L1, L2, L0 is independent from K1, K2, K0. Actually, the group generated by these two vectors, of course, is a free subgroup, a free abelian subgroup of Z2 cross Z3, Z, sorry. So these generate a free abelian subgroup of Z2 cross Z of rank 2. And now, actually, I want to assume that the quotient group by this free abelian group has no torsion. So we can assume, without loss of generality, that the that the quotient group has no torsion, so that's the same as saying it's isomorphic to Z. Maybe I have to replace L1, L2, L0 with L1, L2, L0 plus a multiple of K1, K2, K0. At the moment, I'm not sure whether that's true or not. But anyway, what I'm interested in is the subgroup, not the particular generators. So this is so I'll assume this, and now actually so the set of points which admit a second resonance is dense in gamma. In fact, I mean, gamma's an irrational line, so I can make a rational transformation of R2. So it's really a transformation of linear transformation of Q2 into itself, invertible linear transformation of Q2 into itself, which extends to R2. I mean, they all extend to R2, but you take a rational linear transformation of linear transformation over Q of Q2 into itself, and you assume it's invertible, and then you can transform it so that gamma becomes a subset of say the x-axis, and then of course the elements which admit a strong second resonance are just the rational numbers in the x-axis. So now, if I have a positive number C greater than 0, the second resonance is said to be C strong. If it is possible to choose L1, L2, L0, satisfying all the conditions I've already imposed on it, with the additional condition that L1 plus L2 plus L0 is less than or equal to C. So in terms of transforming gamma to the x-axis and thinking of these things as rational numbers, this is like saying that the resonance, that you have a small denominator. So this is a small denominator condition, if you like. Okay, so this is, and now, obviously, there are only a finite number of C-strong resonances, C-strong second resonances. Now, if the So now I can associate it to a second resonance. I can define another average system. So I'll define so omega, I'll call a double resonance. And so again, I have, this time I have, in place of, over here I had T2 gamma. Here I have T1, call it T1 omega. And this gamma should have been up above. T1 omega is defined to be the set of omega 1, omega 2 tau contained in T2 cross T, such that, well, you have the same condition, but for both of the resonances. So you have K1 theta 1 plus K2 theta 2 plus K0 tau is congruent to 0 mod 1. Same conditions before. And you also have L1 plus L2 plus theta 2 plus L0 tau is congruent to 0 mod 1. Now, and then I have T2 omega. I'll define T2 omega to be equal to T2 cross T divided by T1 omega. So T2 omega will be the state space for the average Lagrangian. And what I'll do, I'll define P omega of P omega of phi equals, it's very much like the definition last time, P theta omega t averaged over theta t contained in phi. Okay, so what does this mean? Just like last time, phi is a coset of T1 omega. So when I'm writing theta t contained in phi, I'm thinking of phi. Phi is contained in phi is a subset of T 2 cross T. So it's a coset. So it has Haar measure, and I can average with respect to Haar measure. So this is the definition of P omega. And I also have K omega. So it's K omega of phi dot, if you like. Let's see. So how to say this? You have a you have a mapping of you have the projection of you have T2 cross 0 contained in T2 cross T, and then you have the tautological projection onto onto T2 cross omega, well, this lifts to R2 R. And R2 omega can be identified with the tangent space at phi of T2 omega. Since this is a torus, there's a standard identification. And now, this actually turns out, this map from here to here, it's a little exercise to prove it, but this map turns out to be an isomorphism of vector spaces. So you have an isomorphism of two-dimensional vector spaces. And so we have the following definition, that k omega corresponds to d2 L0 at omega under this isomorphism. Okay, so this is very much like what we did last time. So I have on R2 I have this quadratic form. I think it's 1/2. Sorry, I have on R2 I have this quadratic form, and then I have an isomorphism, so I can put a quadratic form here, which transfers under the isomorphism. Okay, so and then L omega equals k omega plus p omega is the average Lagrangian. Now, corresponding to this, I have a series of genericity conditions. And these are the revised conditions after I found the mistake. I've written a new announcement. I wrote an announcement in 2003, and I had a list of conditions, and I found a mistake in my proof, so I have to revise the condition. So these are the revised conditions. Let's see. So we have here. We have. One remark is that, of course, this is sort of a constant Riemannian metric on the space. It's at each point of the two torus, you have an identification of the tangent space with R2, or with R2 omega, and so for each point in the tangent space, you have a quadratic form on R2 omega, but all these quadratic forms are the same. So it's a constant Riemannian metric. It's a very simple Riemannian metric. Okay, so now the first condition I have is that let's see, I call it, well, in this new announcement, let's see, so if I have a minimum, so let's consider n contained in T2 omega, a minimum of p omega. And now, of course, at a minimum, the quadratic form, let's see, we have actually two quadratic forms at n, on the tangent space at n. And let me write k omega equals 1/2 g omega. So this will be a definition of g omega. So g omega, so I think of k omega as the kinetic energy associated with this Riemannian metric. Okay, so now I have two quadratic forms, g omega n, and the second derivative of p omega at n are quadratic forms on the tangent space at n to t2 omega. So by, and g omega n is positive definite. So I write greater than 0 to say it's positive definite. It's positive definite because it's a Riemannian metric. And now, so I can diagonalize p2 omega n with respect to g omega n. It's something you learn in linear algebra. And now I can interpret this in this situation as saying that there, and I can choose C infinite coordinates x, y in a neighborhood of n such that g omega n equals dx squared plus dy squared, and d2 p omega n equals lambda dx squared plus mu dy squared. Well, certainly since n is a minimum of p omega n, I have that 0 is less than or equal to lambda, and now I can choose, I can label things so that lambda is less than or equal to mu. Okay, so so I have this result, and now with those remarks, I can state the condition. So the condition is, I'll call it C. Well, in my new announcement, I called C4 omega prime. The prime is to distinguish it from the condition I had in the previous announcement. So this is the P omega has a unique global minimum n omega, and and 0 is less than lambda is less than mu. So here, of course, the lambda and mu are the lambda and mu associated to n omega. Okay, so this is the condition. So for each double resonance, I have such a condition. I'm only going to impose those conditions for C-strong double resonances, where C is some large number to be specified later. Okay, so that's conditions C4 omega. Okay, so now what I do is I set E0 equal to minus p omega n omega. And GE equals p omega plus E times g omega. This is what's called the Jacobi metric. Well, it's the Jacobi metric. It's the Jacobi metric associated to L omega. No, GE, E is a number. E is a number. So for every number E, I have, so this is a one parameter family of Jacobi metrics. And in fact, the only cases I consider, you can consider this for E less than E0, but the only cases I consider are E greater than or equal to E0. Okay, so this is so for E greater than E0, GE is a Riemannian metric. And for E equals E0, G vanishes at n omega. So it fails to be a Riemannian metric at that one point, although it's Riemannian metric everywhere else on T2. Now, also, I need another definition. I need so I have so I'll define H0. H0 equal to the homology class of, let's see, so I want a subset of T2 omega. Let's see, so I erased it, but I had something I called T2 gamma. Divided by T1 omega. And this, I claim, is contained in the first homology of T2 omega with coefficients in Z, which in turn is contained in H1 of T2 omega with coefficients in R. Here, remember that T2 omega is defined to be T2 cross T divided by T1 omega. Yeah, I think I got this right. Okay, so I mean, this is a circle in the 2 torus. This is a 2 torus. This is 1 torus, and the result is a circle containing the 2 torus. So it generates a homology class. Well, it's easy to see it's non-zero. Sorry, so I'll put non-zero here. In fact, it's an indivisible class, of course. So H0 is a non-zero indivisible class in H1 of T2 omega with coefficients in Z. And actually, the way I've written it is not well defined, since I have 2 choices of orientation. And actually, it doesn't matter which one you choose. So just choose an orientation and call the result H0. Okay, so there's a there's this ancient theorem. I think it's due to Morse, as far as I was able to find out by looking at the literature, which is that a GE shortest curve in T2 in H0 is simple. If E is greater than E0. Okay, so, I mean, this is just a general result about Riemannian metrics on the 2 torus. So if you have a Riemannian metric on the 2 torus and you have a non-zero indivisible first homology class, any shortest curve, any shortest closed curve in that, so I should put closed or something. Any shortest closed curve in that homology class is simple. And the mistake I made when I wrote my announcement in 2003 was that I thought the same thing was true for E equals E0, but it's not true for E equals E0. So Yeah, I'm not getting very far to stating the other conditions. But anyway, I guess I can continue next week. So for E equals E0, no longer true. Okay, so this makes things this makes difficulties for my original proof, which I can get around or overcome. Anyway, so I'll impose the condition C5 omega prime, which is that there is only one GE 0 shortest curve in gamma in H0. Now, it turns out that it's not trivial to prove, but there are just three possibilities. Gamma is simple and does not pass through in omega. So 1, 2. Gamma is simple and passes through in omega. And 3, let me put this on another board. Gamma equals P gamma 1 plus Q gamma 2, where P and Q are relatively prime positive integers. Gamma 1 and gamma 2 are simple closed curves that pass through in omega, but do not meet elsewhere. And gamma 1 and gamma 2 are shortest curves GE0 shortest curves. And homology classes H1 and H2 and these homology classes generate H1 of T2 omega with coefficients in Z. Okay, so those are the possibilities. Now, I guess my time's up. I'm sorry to leave you hanging in the middle of the discussion here, but I'll have to. I guess next time, at the beginning of next time, I'll give the other conditions that genericity conditions defining U. So these are all conditions defining the set U. In other words, I'm going to, U will be the set of Lagrangians which satisfy these conditions, and it'll be fairly obvious that they define an open dense set, and then V and W will be defined in terms of U. Okay, so I'll stop here for today.